Hey, if you're here from Matt's video, welcome. Matt said that I would show you a video of how I built some things, and so I will. If you're here not from that Matt's video, welcome. Maybe you're watching because I've done another Geogebra build. This is one I was asked to build by Matt for his video he's just released. So let's go through, to be honest, the somewhat basic stuff that I did to make the graphics, and I will also try and show a little bit of the Python I did, which got some of the graphics on his video at the end. And I'll say right here at the start of this that I am not a Python expert, so don't at me as Matt and other people will say. I'm an amateur at Python. What I really like about Python, and indeed about Geogebra, is that even amateurs can get good results quickly, and that's a really nice thing. If you can build something yourself, you start to understand it more. I even pinned that on the wall behind me as a quote from Richard Feynman. If I cannot build it, I don't understand it. So let's try and build this. So I'm going to dive straight into Geogebra Classic 5 here on the screen. One thing to get out of the way first of all is that you can, if you're going to talk about the gamma function, which is what really Matt's video was about, the gamma function is built into Geogebra. So if you just type gamma, there's a whole bunch of other stuff in here. The one I'm interested in for this, I'm not going to talk about the rest. The gamma distribution is a different thing. The gamma function, gamma of x, go and look up what the other things on here are if you're interested. But gamma, if I press return on that, I could put a particular number in, or I can just put x and it will plot the gamma function. That is most of the work done. The gamma function is built in. Now, word of warning, what Matt talked about a lot in the video that he made about factorials or generalized factorials is pointing out that the gamma function is not the same as the factorial function. It's shifted by 1, and we'll spend some time showing that here and maybe show you the shift as well. But the gamma function is built in. It even has the little capital gamma there, which is nice. Let's focus on getting a plot of the factorial numbers for the whole numbers first, and then we can talk about whether these line up and just tweak that. So I'm just going to do some zooming in. The factorials grow really quickly, so off here is kind of irrelevant. So I'm just going to hold down shift and drag this to stretch it out there. And off to the left is interesting territory, but we're just going to get the positive integer territory sorted first of all. You'll notice that 3 factorial should be 6, but it's 2 according to this plot, and actually the 6 is up there, and that's because of the off by 1 error that we discussed. So let's get some factorials plotted. Now I could just type in the coordinate 1, 1 for the first factorial, but let's do it as a sequence. I seem to be just doing sequence commands by default when I work in Geogebra these days. The sequence command is really powerful. I would like a sequence of points, not just the values, because I want them to plot. So let's get a coordinate, and it's going to be, I need a dummy variable here, let's use p. And then p on the x-axis and p factorial, which is just exclamation mark in Geogebra, on the y-axis, and I need to then tell it to run p from, let's run from 0 to n. Now I haven't told it what n is, but because of the way that the syntax of this, it's going to ask me, I think, for a slider for n, and I can tweak it. I probably should make the slider first, but I can always go back and change it afterwards. And lo and behold, it's asking me to make a slider for n. And here we have n. Oh, it's made a slider for p as well. This sometimes happens. P was a dummy variable. If I delete it, nothing will happen. Better to make the sliders first so that doesn't happen, perhaps. Anyway, I can drag up n, and I get some factorials being plotted. That's nice. I'm also going to limit n, the slider, to be from 0 to 5 is probably plenty. Go up to 10 and go up in ones. Now, if I'd made the slider first, I would have done that first, and then I wouldn't have had to deal with random numbers in between numbers. As it is, this is just how many factorials to plot, and it's counting 0 as one of them. But that's probably going to come back to bite us later on, because when n is 3, we've got 4 points. More on that in a moment. But that's just the factorials plotted. You can see the curve is not going through that. So let's deal with a few things. In the video, we talked about how to, if you only had 2 points, say these two, you could draw a line through them. 2 points, straight line. 3 points, you could plot a quadratic through them, order 2 polynomial. 4 points, you need an order 3, a cubic. And actually in the video, what we did was show a plot of some possible other definitions of how to generalize the factorial. So let's do that first before I come back to the gamma function. Actually, I plotted a straight line between these two in the video. And then we sort of let it go on a bit, and I showed a plot of something went through the first few points. I left out the 0 point because we weren't talking about 0 factorial. We didn't want to go into 0 factorial and why it is 1. There's a very good reason why it's 1. which is kind of partly why the gamma function exists. Like, how do you deal with factorial functions of factorials of numbers which aren't so intuitive? And actually, in the video, I didn't use the 0 point, so I'm going to adjust our list so that we don't have to deal with that. I'm just going to let it start from 1. I'll put that back in later on. And what I think I did is I let this, so 4 was on screen, I actually let it go to 5 or maybe 6. Let's see. The command I'm going to use, though, to fit a line to this is called fit poly, and it doesn't fit a line, it fits a polynomial. Fit poly, it wants a list of points. I'm going to give it L1, which is the list I've just adjusted there, and I'm going to need to tell it the degree. Now, with, let's get this right, with 2 points we need order 1 polynomial, a line. With 3 points we need order 2. With 4 points we need order 3. So with 5 points, and I do actually have 5 points now because I've deleted that 0th point, I need order 4, and you can see that is going through those points. If I gave it a lower order polynomial to try and fit, like a cubic, you can see that it tries to fit it and it does okay, but it's not getting it exact because it can't satisfy all the criteria. I think it's doing a least squares fit, but I don't know, I haven't checked. And if you don't know what least squares is, internet exists, go look it up. However, what I want to do, maybe let's just make this change with my slider. So I'm going to say n-1, so it will fit however many points I've put in there. And in the video, I think I let it go to 6 because this is obviously not a good attempt to approximate the factorial function for the bits in between. Why would it go up and then down? But it is hitting all the points, and it's actually also hitting the point up here at 5,120. That's so far off the top of the screen that we didn't bother showing it. It's kind of hard to fit everything on the screen when you're dealing with factorials. Good enough. And I think we just dragged that on screen so we can see the polynomial that does it. It's obviously not the right function, but it does fit the first 5 points. 6 points, I think. Yeah, 6 points. But I didn't put the 0 in. So actually, I'm just going to get rid of that. That was our attempt to find a function which goes through the points, but it's not the right one. If you have the other criterion that Matt talked about, which is to do with the fact that factorials work by the next factorial is the previous one multiplied by the next number you're at, then you come up with what they call the gamma function. Except it's not the gamma function because the gamma function is over by 1. And if you don't believe me, let's just turn this back on and you can see it's not fitting. However, I've called this gamma function f in the way I've defined it. If I just define a new function, which is f of x, plus 1, you can see that's shifted it over. And actually, if you wanted to make that a shift, instead of calling it plus 1, you can just say plus a in there, get a slider, and you see that sliding the gamma function around gets you exactly to what you want when it's there. So that is the gamma function shifted left by 1, or gamma of x plus 1. Nice A-level transformations or GCSE transformations there. And this gamma function is going through the factorials, and there's all sorts of deep reasons, which I'm not going to go into. Matt kind of did a bit of that, and other things are available to investigate that. But that's why the gamma function is an approximation of the factorials, and you can see that it goes between them in a sensible way. It does do interesting things at numbers less than 0. But it is making 0 factorial 1. And remember that this gamma of x plus 1, or the factorial function, is not the gamma function. It's just the same though, as it's just shifted over. So that's kind of what I made the graphics different. I made the lines thicker and I made the background black. But essentially that's what we got here. The other things that you might be interested in with Geogebra to play with, I just realised I've got this slider which I now don't want. Tell you what, let's just change this back to 1. And that is my factorial function. I don't need a now, so let's just delete that. Fine. The other things I did in the demo is make the line animate. And it's useful to know how to do that in Geogebra because there's a very nice command called function command. So if I type in function, it says, do you want to, you can make a function out of a list of numbers. Not this time. I want to use the function command, which takes a function and then a start and an end value, and it limits the domain of that function. So I'm going to use the function g, which is the shifted gamma function, or the factorial function, if that's what we're going to call it. Thanks, Matt. And I'm going to let it start from 0 and run up to something I could animate. So I'll need a slider. I'm going to use a again because I deleted that earlier. We'll make another slider for a. Thanks. And let's make sure the a slider has some properties which I want. I want it to start at 0 and maybe go up as far as n. And I want this to go up kind of smoothly, so I'll just make sure it has a small increment. And you can see that that is sliding something. Maybe I'll turn off the g function. So now all I've got left, I'll turn off the label. I've got an adjustable sliding function. So watching a function slide along, I could just right-click animate this, which is pretty much what I did off screen when we were making the graphics, and you see this function animating. That's a really useful way, by limiting the domain, to make functions animate. And it's going to come bouncing back unless I change the properties of this, which I'm going to do here. Make it increase just once, so that it just animates once. Maybe I'll make another one to show the negative side, and that's dead easy. Let's make a new function using the function command. How shall I do this? I want the same g function, but this time I want it to start. It works from left to right here, but it's the left value I want to change. So let's say it starts from negative b b is a slider I'll throw in a minute, and goes up to 0. It'll ask me for b being a slider. Fine, I would like b to be positive because I'm putting negative b into it, starting at 0, going up to... It doesn't really matter what it goes up to, and I'm not even going to change the increment. It picks something sensible if you're not too worried about it. And now we've got a way of sliding the negative things. And actually, if we zoom out a bit, you can see the negative values of the gamma function in all its glory. And it has a few problems down here because the precision that Geogebra, which is a numerical package, not an analytical one in the end, these things are shooting off to infinity very quickly. So there's some sort of singularities going on, which it doesn't really like drawing. So that's why we kind of left it cropped over here. So that's pretty much what I did, and if you wanted to animate, you can see that going in. So if you set it both to 0, you can animate the right-hand side, or you can just right-click it and let it animate. Off it goes, and I can right-click and let this animate to go that way. Maybe I want the label off on that. If you are doing animation on Geogebra, it's quite nice to realise that at default level, a slider takes about 10 seconds to complete itself. So when you go into properties, that speed 1 means about 10 seconds for a full oscillation, a full journey across. And that's how you can get an approximate sense of how long things are going to take. That's pretty much it. But as Matt pointed out then, you begin to see a picture of the gamma function now and think that left-hand side is interesting, so this region over here. And it does look surprising enough that you start to wonder if we're not sort of missing the bigger picture, as indeed we are missing the bigger picture, because if you plot this on the complex numbers instead of just that real line that we're looking on now, you see why that landscape, or you see more of the landscape. I'm not sure you do see why the landscape is what it is. That's a deeper question, which I'm not going to pretend to answer. But it would be nice to be able to plot the surface in Geogebra, and I couldn't make it happen. I was defeated. Geogebra didn't let me plot the complex surface. Now, that's not because Geogebra doesn't know about complex numbers. It does. It's because the gamma function built into Geogebra doesn't seem to accept a complex argument. And let's look at that a bit more closely. Complex numbers are fine in Geogebra. In fact, if I just type one in, 1 plus I, it'll even turn it up. It'll start assuming that the diagram we're looking at isn't just a graph axis. It actually, the horizontal is real and the vertical is imaginary, which is kind of a superposition of ideas. But Geogebra understands complex numbers. What's annoying is that if I type gamma of a complex number, I just want the normal gamma function here, 1 plus I, doesn't like it. Illegal argument, which is a bit odd. I don't know what's going on here, and I haven't checked in the innards of Geogebra or written to the developer about why gamma is not accepting complex numbers, because it could. And other functions do accept complex numbers. So if I type in the Riemann zeta function of 1 plus I, this is built in functions Geogebra as well, it'll compute it and it'll give me the answer as a complex number. So that's fine, but the gamma function doesn't work like that. If you are interested to plot a surface in Geogebra, it's worth just having a brief distraction on that. We did this in another of Matt's videos on the Fibonacci, complex Fibonacci stuff. So let me quickly show you how you can plot surfaces really quite easily in 3 dimensions in Geogebra, and then I'll show you how I did the sort of quick and dirty Python things that we used in Matt's video. So let me just turn off these functions for now that we don't really want to see. I'll turn off the points as well. In fact, we're going to ignore the graphic. I'm just going to close that. You can always bring these things back from the view command. So here's just a blank 3D window, but the gamma function doesn't work for this. So I'm going to show you with the Riemann zeta function, and the easiest way to plot a surface in Geogebra is to just define a multivariable function. That sounds complicated. Just a function instead of depending on one variable that defines on more than one. I need to call it something. I'm going to call it S for surface, and I want it to depend on 2 variables. I'm using capital X and capital Y to avoid it getting confused with the built-in variables of X and Y that we'll try and plot with. It might work with that, but I'm not too worried. I'm defining a function based on X and Y, and it's tempting just to write zeta of the complex number X plus IY. You can see it's doing something already, but we have a problem in that it doesn't know how to plot on as a surface a complex number output. And this is the problem that Matt discussed. You need a 4-dimensional graph to plot 2 dimensions input and then a complex output which has 2 dimensions. So we need to reduce the answer to the zeta function to a single number. So one classic way is the absolute value, or the real value of it, or the imaginary. Let's just do the absolute value. So I'm going to grab the absolute value of zeta, and there it is. By default, if you give a multivariable function which depends on 2 variables, it will try and plot it as a surface, and I can spin it around if I make sure so it's already got that strange looking bit of the zeta function. And if I scroll my mouse wheel, it's doing quite a lot of work here, trying to sample all these points, and I didn't tell it how much to sample. You could give it a more detailed surface command to do it, but you can see it is doing pretty well. When I zoom out, it is trying to capture some of the strange behavior of the zeta function. It's just nice to know this is available to everyone. You can see The random spikes that happen in the zeta function are beginning to become more obvious there. We have some similar spikes actually in the gamma function, and these things are connected like most things in maths. Anyway, we can plot nice surfaces from complex functions in Geogebra, but not the gamma function. And I tried defining it as the integral itself, but it just needed so much computation work that actually it's very, very slow to plot and really fiddly to do. So at which point we resort to another package which has a built-in gamma function, just like Geogebra has a built-in function, but Python also has if you get the right library, and it can handle complex inputs. So we just did that. So let's have a quick look at the quick and dirty Python we did for the visualizations at the end of Matt's video. In the spirit of these videos, I'll try and do this live, but the nature of coding something in a proper coding language like Python is much less visual and more, in my case, feels ad hoc and fiddly to see what's going on. So this is going to be less visual, and you'll see probably lots of messy coding. I'm not taking this as a good example of how to code. I feel really very much an amateur when it comes to actual coding. I feel like I'm out of my depth, but we all have a bit of imposter syndrome. So first thing with Python, the first thing you can tell I'm amateur. I'm not doing this in VS Studio. I could do, and I have that installed. I'm just working in the Python shell and the IDLE, so I can open, I can get a new file, which is off screen here. This is just a file which I could save, which will run. And this is like the most basic way that I can really see of editing Python things. And in some ways I kind of prefer it. I'm not having to run a whole program to edit with, but then you have downsides in that maybe it doesn't auto-complete things as much as you'd like. I feel like a complete noob, but I can still get something done. So with Python, the first thing to realize is it basically relies on libraries that you have to import. So you do that. There's a whole bunch of libraries I'm going to try and import, and I know I need some 3D graphing for this. And the way I got that, basically I just Google this every time I want to figure out what I want, and you just spend if I start coding in Python, I know I'm doing it because I've got 300 tabs open in Chrome to find out all the things I've just Googled. But from MPL Toolkit's mplot3d, I'm going to import axes 3D, and that command will get me some 3D plotting tools. And I'm going to, there's some pretty standard imports. I'm going to get matplotlib.pyplot. I feel like these are things which go at the top of every Python thing I use. And let's also, because I wanted to get an animation out of this, matplotlib.animation, let's get animation. So these are basically shortcuts. I can use that matplotlib.pyplot as PLT, and I can use matplotlib.animation as animation. That's what that's doing. And I'm going to import from NumPy, I presume that's how you say it, as NP. That handles arrays in a sensible way, in a way that I feel sort of comfortable with. And I'm going to get, this is the bit that gets me the gamma function. So SciPy, I presume it's special, apparently. I had to go and dig this one out. Import the gamma and the factorial function. I don't think I used the factorial function, but I imported it just because. So those things are built into SciPy. They're probably built into some other things too, but for some reason I think I felt like I had to use the SciPy one. Maybe it's the only one that handled complex numbers. Once it starts working, you stop worrying about whether there's another way to do it. So feel free. You could tell me all day in the comments about better ways of coding. I know there's a better way. Knock yourself out. I won't necessarily read them all. But it's a strange thing. Like coding is one of these sort of Heath Robinson is the British way of describing it. You just kind of bodge it all together, and if it works, you stop worrying about it. And then, to be fair, debugging it becomes a nightmare, which is why having good coding practice as you go is sensible. Yes, Ben, you should have good coding practices. Right. So let's deal with a few sort of practical things. I'm going to create this. This is the way of making a figure. So fig is going to be plot figure. Let's do that. Bracket fig size. And this was just me making it fit the right size. So there's some kind of conjuring out of nowhere, but I wanted it to be high res. So I actually did change the DPI in there. I'm not going to bother with this. And this is the bit that I found to get a 3D axis, is let ax equal fig.gca, and the projection equals 3D. I'm pretty sure I copied that and pasted it into my code from an example on a website. This is pretty much how I write a lot of code. You go and find something which does similar to what you want, and you paste it in and then debug it because it's not working and you haven't imported the right libraries or something. But this one worked. And then I had a bunch of other commands which I added later on. I'm not going to do them yet to sort of get the aesthetics right. But then now we're going to get to the sort of fairly basic meat of this. I want to define the x and y lin spaces, or like the array we're going to work with. So the x, I'm going to run, it's an NP, a NumPy array. A linspace is a command that sort of divides up a space into bits. I'm going to run from -4 to 3. And I'm going to do, I think I did this in lots of jumps. So I'm going to do just in 100 jumps to start with. So it's dividing between -4 and 3 and 100 units. And y, I'm going to go between something similar, but this one I think I wanted it to be more symmetrical, to go between -3 and +3. And we'll do that on 100 steps as well. And actually changing the number of steps there might give us a more detailed graph or a less detailed graph, depending on the increase or decrease later on. And finally, to make that into a grid we can use to plot a surface with, you can get a sort of two-dimensional command called np mesh grid. So numpy mesh grid grabs those linear things and turns it into a mesh, a grid which we can use to get all the combinations, like a two-dimensional array there. Again, I feel a bit out of my depth about how that works, but it works. So a lot of people say, well, there's a quote about mathematics, you don't really ever understand maths, you just get used to it. I definitely feel that about maths, and even more about coding. Like, I don't really understand these, but I'm used to them, so I don't panic when I see them now, but I haven't really sorted out exactly what they're doing in my head. So I've got the x and y. I need to define the surface to plot at those x and y points, and that's kind of like what we did in Geogebra. It's like the just define a multivariable function. We've got all the variables to plot it over, so let's just say z is this is where the gamma function now exists. I imported it from SciPy just as gamma, and this is where I had to do a little bit of digging about how to enter a complex number. First of all, I want x plus iy. I think I typed that first. Didn't like it. It turns out it needs j, and it turns out it needs 1j. That's the unit of the imaginary unit. I'm out of my depth. I'm not sure why that worked when I used 1j, but that seems to be how I type what I think of x plus iy. X plus 1j times y. Now, I'm very used to calling j the imaginary unit because the exam board I used to work for called it for a while, but I feel like I'm much more comfortable calling it I. Looks like this package wants to use j. Hey, if it works, I'm going to use it. So that is the gamma function, but the trouble is with that is it is probably a complex output. So there are two problems. Like, one is we might hit some of these infinite spikes as well, and we're going to get things which are not a number, and that might be a problem too. So first of all, I'm going to create the absolute value for that. So the absolute value is a function. I'm going to autocomplete for this absolute value of that, and that should give me a real number output. And I think that's it. I expect we're going to get an error message because of the infinite spikes, but let's see what happens. I'll come and tidy that up in a bit. And now I want to plot the surface. So I'm going to call this surf, and the command, which comes from the axis command, I think, is plot surface. And I need to tell it the x and the y and the z. Those are the three coordinate sets that I've defined. And then I think you can... I'm just going to leave all the colors out. In fact, I might just leave it as it is. That's the basic command, and we'll add in some detail in a bit. And then I think all I want to do is... I'm checking what I did, my notes here. I think I just want to show the thing. So let's just do that. Is it show plot? Let's check. I've now forgotten temporarily how to actually just show the plot. How do we just show a plot? It's hilarious how rubbish I am at remembering Python. I spend most of my time just Googling how do I do the basic thing again? How do I just do the basic thing? Plot show. So I take the plot thing, or pyplot.show is the command. It doesn't take any arguments. All right, that's it. I haven't even saved this file yet. I have no idea if it's going to work. I've been prattling away. So I'm going to press F5, which will save this. It's going to ask me. It just popped out that dialog here. Source must be saved. Okay, I've got it. It's going to ask me where to save it. As you can see, this is my folder of random Python scripts. Let's do the live build gamma plot.py, and then it's going to run it. What errors are we going to get? Don't know. It's thinking about it. It's thinking maybe I've given it way too much resolution. I don't know why it's not. Oh, it's popped up something. It's over here. Oh, there we go. I'm dragging this on. That's what just popped up. And that's kind of what I wanted. Now, the first thing I didn't realize about Python matplotlibs is that these are interactive diagrams. You can see the coordinates are moving around as I drag, and it's even giving me an idea of the height, the Z command, which disappears when I go and point at it, and I can't point at it with my finger, and I can drag it. So this is just left drag, and I can move it around, and I can scroll the wheel. Can I? No, it's a right drag zooms in on this, and actually this is kind of what I love about Geogebra is interactive, and I hadn't realised that Matplotlib does this. There are some problems with this. That's a right drag there, and a left drag seems to spin it around. The heights of these spikes are sort of dominating everything. Actually, I want to kind of see more detail, and this is going up to 20 when most of the detail is much lower. So what I want to do is kind of clip the top of these things. But already we've plotted the surface of the gamma function. This happens to be the absolute value. So maybe let's just do some tidying up. If I close that, it finishes there. I'll go back and adjust this. I think I found a command which clips numbers. So I want to limit it. Don't go up as far as looks like it went as high as 20. So let's just clip it to something smaller. So what did I call it before? I think np clip, I think, is the command I'm after. So for this thing here, I'm going to put that in brackets, and I want to clip that thing. I trim the top. So np clip was the thing, and it takes an argument that it wants to know how low to clip it and how to. Now I don't think that, because it's an absolute value, it's never going to be negative. So I'm just going to put 0 and let it go up to maybe 10. Just to, if anything goes higher than 10, it should chop it at 10, and that might deal with any not a number errors as well. I don't actually know. Maybe we've dodged any of the exact points that cause the errors. Let's just run that now. It seems to take a while for this to run. Maybe that's because I'm doing lots of points. Unmatched bracket. You didn't. I've got to close my brackets here. Maybe that's better. Ah, such a noob at Python. Unmatched bracket. Have I done too many brackets now? So yes, I have. There we go. I think that's sorted it. Let's run that now. Doesn't like that. What's going on there? Invalid syntax. Maybe I haven't closed my bracket now. That's better. Is that better? Abs takes one argument, so I put the brackets in the wrong place. So the abs needs to be closed there, and that one needs to be closed there. I thought that's what I'd done before. Let's try it. It's running something. Oh, it was much quicker to plot it that time. Maybe because it wasn't computing really large values. It's still quite high for the spikes. I might want to clip it a bit more, but we can get a little bit better surface idea. So I'm just gonna. This is where you start repeating. So I'm going to clip it right the way down. I think I even clipped it to 5 in the video just to get most of the detail. Let's just run that again. Once the bugs are out, you can just keep running it. And now that's actually much more like the plots that we were showing in our diagram. And you can see those loops that turn up on the negative places here are kind of what we were seeing. But as Matt pointed out, taking the absolute values, kind of removing some of the information. It's pretty easy though to go and get the other versions of this. So I can just go back in here. Instead of getting the absolute value, I can just delete that and take that thing, which is in the brackets there, dot real. It took me a while to figure out how to do that as well, but that thing is a complex number, and if I get the real component of it by doing dot real, I think it'll still do that, and it's still going to clip it between 0 and 5. And actually I might need to let it go down because it might be a negative real number. Let's run that and see if I've messed up that. Oh, there we go. There's the real plot. And this is great because this is actually one of the plots that we showed in the video, and you can begin to see how easy it is to make these plots. Now, the only other thing we did on the video was make this animate so we could get a clean animation of it spinning around. But actually, to be honest, it's much more fun to be interactive with it and just move it around. With a 3D plot, I think it does need to move because essentially we're seeing a 3D diagram in two-dimensional screen. But as soon as you move it, a kind of an illusion of the third dimension comes back, and it's almost like you can get your hands on it, and that's why moving three-dimensional images is really helpful. And if you can't move it with your own mouse or hands, then just having it spin is great. And in Geogebra you can just drag the thing and it'll keep spinning, or click the spin thing, and in Matplotlib you can just drag it. So I hope that's got the basic idea. This is not a complicated bit of code, and I'm sure there's better ways to do it, and I haven't put any comments in, and that's terrible. You could add some colors. The surface command could take a color map. You have to import a color map package, but all those things are aesthetic. Just the basics there. It took me way too long to find out that I could do it, but then when you get down to it, it's a simple piece of code to look at a really nice piece of maths. So there we go. I hope you've enjoyed seeing the way I built the Geogebra file we used in Matt's video and the Python files. Remember, I'm a rank amateur at Python, so I'm not claiming that was particularly good code, but I really like the way that Geogebra and Python make the sort of ability to explore mathematical landscapes, almost literally in this case, democratically available. Anyone can do it. All it takes is a bit of perseverance and learning the skills to do it. And they're not that difficult. These packages like Geogebra and Python and everything else, Desmos, Autograph, are brilliant. I'm really glad they exist. And I get excited exploring these things. So I hope you've enjoyed learning how I did it. I'm not claiming they were particularly expert. I want to thank Matt for asking me to contribute to the project. I really like working with Matt. He's always got an eye for nice bits of maths to explore. I really like working on visualizations like that. So thanks, Matt. And I'll be doing more of these live build videos and some other videos. I think we've got time to do another exam video sometime if Tom Crawford's up for another rematch. Whatever. If you've enjoyed it, then I'm glad. And hopefully I'll see you next time.